Oh, thank you. I'm very pleased to be here. So uh, first of all, I have to thank Henri Hollande, my good friend, for inviting me to come spend a year in Paris. So, as some of you know, I spent a year in Paris 23 years ago at the École Normale Supérieure, at which time I taught a course on something else. And so I'm very pleased to be teaching a short course on group theory for physicists. So the emphasis, first of all, immediately, is that this is group theory for physicists, not for mathematicians. So those of you who are looking for mathematical rigor should not be in this course. So maybe it's so important that I would write it down on the blackboard. I'm going to use the blackboard, not the PowerPoint. So not rigorous. So when I've never spent any time at any extended time at Caltech, and I've only met Feynman a few times, unfortunately. But I was told that when Feynman teaches a course, when a student asks a question of mathematical rigor, Feynman would just go like this, which means he's just pointing in the direction of the math department. And she always go there. So when I'm teaching in the University of California, I do the same when students ask me a question about mathematical rigor of very rigorous proofs. I just go like this. But here, you don't even have to go to the math department, just in this building. Could ask Kiron for mathematical rigor. So the course is going to be based on my book, which some of you may have seen, Group Theory in a Nutshell for Physicists. And this book itself is based on a course I gave at the University of California. I gave it twice at the University of California for 2 years in a row. So this book just came out. And in fact, I taught this course last year, but it just came out several months ago. It came out in 2016. So I'm going to be more or less following this book in detail. So perhaps I could show this. People would like to look at this book and pass it around. Okay. So obviously, in 5 weeks, I'm not going to be able to cover an entire book like this. So I thought I should focus on a particular topic. So I'm going to talk about the Cartan classification, especially since I'm in France. I should talk about the Cartan classification and Dinkin diagrams. But I really don't know what the level of the students are here at the University of California. This course was given to beginning graduate students and advanced undergraduates. So some of these people are seeing group theory for the first time, but here the students are allegedly more advanced. So I'm going to assume, so this is what I assume that you know. If you don't know that, then maybe the course is not suitable for you. I'm going to assume that you know what a definition of a, sorry?
Not fully, I am not physicist.
Oh.
I'm just graduate.
You are a?
Engineer.
Well, we'll see. You discover. So I would.
I will try to follow.
You would try to follow. Good. I think effort is very valuable. So I'm going to assume. I'll assume. What is this? Students needing a final certificate, please contact the organizer.
This is my business.
Oh, okay. So you have to sign some documents.
Yeah.
Okay. So this is what I'm going to assume you know. That you're going to, you know the definition of a group, so I'm not starting from page 1. Obviously, it's impossible. The book is almost 1,000 pages. So you know the definition of a group. You know what a continuous group is, finite group. And you also know the definition of a Lie group in the Lie algebra. And you have, you know what a representation of a group is. Okay, so that's what I would assume you know. So I always tell my students when I teach that ignorance is no shame, but stupidity is. So if you're ignorant and you don't know this stuff, then the course is not suitable for you, and you should not take this course. That's not no shame at all. You should. And of course, some people could, even if they don't know some of this stuff, they could learn it very quickly. Okay, so this comes to the question of pace. How fast do I go, and so on. So I need to find this by trial and error. Okay. So now, and I also have no idea about how French students compare with American students. So I tried to find out from Philippe DiFrancesco the other day, because he had been teaching at the University of Illinois, and how the two kinds of students compare. So perhaps it's not inappropriate then to mention how theoretical physicists and biologists compare, because when there was a famous story that when Delbruck first wanted to switch from physics to biology, he asked famous biologist Oswald Avery, who later won the Nobel Prize, and Delbruck later won the Nobel Prize in biology also. And Delbruck, you probably know, did quantum field theory. And he asked Avery to come give some lectures to the theoretical physicists about biology. And Avery asked Delbruck, how much do these theoretical physicists know? So he said, well, they know almost nothing, but they're infinitely intelligent. So I was told that French students are like this. They are infinitely intelligent compared to American students. So so I would go slowly at first, but we need to find out by trial and error. So please ask questions if there's something you don't understand, or if by questions and discussions I can have a feeling about how fast I should go. So here's my plan. My plan is that for this course is that I cannot suddenly start with Catan and Dinkin. So I will start with SUN, and very quick review of SUN, and then I'll discuss SU2 and SU3. And SU3 is really how physicists first got a glimpse of the Catan classification. Okay, and since the and even though I mentioned that I assume you know the definition of a group, since there are many students here, I will give the definition anyway very quickly. So I think most people here know that a group G consists of a set of elements, G alpha. Alpha is some index, which may be discrete or continuous. If it's continuous, then it's a continuous group. And such that G alpha, G beta, there's an operation called dot, which is we think of as multiplication, such as G alpha, G beta is another element, G gamma. And this dot will omit and just write G alpha, G beta. So this is a group if it satisfies three properties: associativity, G alpha, G beta, G gamma is G alpha, G beta, G gamma. And identity, that there exists an element called I, okay, such that I, G alpha, is equal to G alpha I. And inverse, that for each group element, there exists something called G alpha inverse, such that G alpha inverse G alpha is I, and it's the same as G alpha inverse. Okay, so anything that satisfies these properties is known as a group. And of course, the important thing to notice is that commutativity is not on this list. It may or may not commute to the group multiplication, so rotation is a famous example. Now, I trust that everybody knows this already. So if you, as I said, if you never heard of this, if this is completely news to you, then maybe it's not, the course is maybe not suitable for you. Okay, now there's actually an interesting little known fact. So even though I start with the definition, which may bore some of you, I can tell you one interesting small fact, which may not be as well known as it might be, is that actually 2 and 3 could be weakened. We could weaken 2 and 3. So this identity, this statement here says this object is the left identity as well as the right identity. So if you multiply on the left and multiply on the right, it gives the same result. And it can be weakened to 2. 2 can be weakened to 2 prime, and 3 can be weakened to 3 prime, in which you say that the inverse is only a left inverse. That is to say, for any g, there exists an f such that fg is equal to I. So given this, you can actually prove that the left identity is also the right identity, and the left inverse is also the right inverse. So in fact, this is a good exercise for the students who already know something about group theory to try to prove this. Okay. Now in physics, the idea of a group comes out very naturally as transformation, because in physics we have the notion of transforming the laws of physics. And so that the transformations naturally obey the axioms of a group. Okay. So as I said, I'll start with a review of SUN. How do you move this thing down?
Just virus.
Oh, okay. Just by brute force. Okay. Okay. So as I said, I'll start with a review of SUN. So that's extremely. And I would refer to the page in my book. Okay. So for those of you who I of course cannot give all the details. So for the details, I refer you to the group. So let me remind you, UN corresponds to the set of n by n matrices with complex entries, and U dagger U is equal to I. And here's my notation. I use standard physicist notation. Dagger, which is the Hermitian, known as the Hermitian conjugate. Of course, named after the French mathematician Hermite, which is complex conjugate and transpose, which is of course the same as transpose complex conjugate. So transpose a matrix and then complex conjugate. So you check that if U1 and U2 satisfy this property, then U1, U2 also satisfy this property. Okay, so that's the definition of UN. But the deep mystery, which I don't think anybody actually understands, is the relationship of quantum mechanics and complex numbers. So physics, we could have done physics without complex numbers, with only real numbers, until quantum mechanics came along. And this is a deep mystery, why complex numbers come in.
What do you mean before
Sorry?
Before complex, what did you write?
Oh, N, sorry. Okay. In France, you use the same symbol?
Yes.
Yeah, okay, sure. Okay. So in fact, earlier this week, I was, in France, there are a lot of people who do finance using random matrix theory. And so these people who do finance were telling me I was doing unitary groups. They don't care about unitary groups because nothing in finance is complex. Everything is real. That's the joke. Okay. So, but in physics, we are left with this mystery why complex numbers and unitary matrices are relevant. Now,
What do you mean when you say it was not obvious that QM reduce complex numbers?
I'm sorry?
You said complex numbers were not obvious going to mechanism.
Well, in classical physics, we don't need complex numbers. So as you know, mathematicians have these so-called division algebras, real numbers, complex numbers, quaternions, and octonions, and so on. And as you know, classical physics can be done strictly with real numbers, and complex numbers don't come in. But it's only as perhaps a helpful mathematical trick. But in quantum mechanics, complex numbers seem to be essential. And so in fact, why, and so on and so forth. And the obvious question is that some people have investigated is whether quaternions would be the next step would be to introduce quaternions into physics. And I know people, Stephen Adler at Princeton, for example, had spent 25 years of his life trying to introduce quaternions into physics. And he wrote a book, but I believe most people felt that he failed.
Who did you say?
Sorry?
Who was it?
Adler. Steve Adler. He has written a book. Adler. I mean, he responded to this. Okay, so let me move on. There's a famous subgroup, and again, I'm not defining any of these things, so I'm giving roughly the level of the course. You are expected to know what a subgroup is, and so on. The famous subgroup is, of course, SUN, which is subgroup of UN. It is when you add this extra condition that the determinant of U is equal to 1, then the collection of all matrices which satisfy this as well as that is the subgroup SUN. And the determinant of U1 is determinant of U1, determinant of U2. So this says that it's consistent with the group property. Okay. So again, for the students and for the people in the audience who are bored with the course, with the lecture so far, that it's kind of at this level, you could try to prove this in your head. And okay. All right, now here is a side remark. Again, this is maybe to maintain interest in some of the more advanced students in the class. As you know, SUN plays a very important role in physics. And in fact, physicists often write U2 is equal to SU2 cross U1. We all know the Weinberg-Salam model, the standard model, is based on SU2 cross U1, the unification of electromagnetism and weak interaction. And of course, we also have the strong interaction is based on SU3, quantum chromodynamics, and people use SU5 as grand unified theories, and so on. So this is what physicists usually write, that U2 is SU2 cross U1. So again, so just for the people not to be completely bored, is that I want to remark that this, strictly speaking, is not correct. So in fact, so if you open, if you are very strict, many things that physicists say are not correct. Okay, so it's not correct at the group level. The reason is that if you write the direct product of a group F and G, F cross G, this group is supposed to consist of elements F, comma G, okay? And the multiplication rules are the obvious ones. F1 G1 times F2 G2 is F1 F2 G1 G2. Okay? And it has obvious subgroup. It has two obvious subgroups. One of them is F, all the elements of F, and the identity of the group G, which I'll be pedantic and put a subscript to show that it's actually the identity of the group G. And the other subgroup is, of course, consists of the identity of F with G. Okay, so these are two subgroups. And we see that the only element in common between these two subgroups is IF and IG. So that's the definition of direct product. But when physicists write this, it's not quite correct, because you think of UN, okay, and you write UN, then the subgroup U1 corresponds to elements of this kind, e to the I alpha times the identity matrix, where e to the I alpha is a phase. And SUN, as I said here, corresponds to all the things with determinant u equal to 1. So if u has the form e to the I alpha 1, e to the I alpha n, with 0, okay, then if e to the I sum over alpha, the determinant is obviously, the determinant is I sum over j alpha j. So if this is equal to 1, then this belongs to SUN. So therefore we see that this set of elements, e to the I pi kn times identity, k from 0, 1, and so on to n minus 1, this belongs to both groups. So it's not a direct product, right? So if e to the I pi k, if k is an integer, then it obviously satisfies this and also satisfies that. So it's not a direct product, and in the sense of F cross G. So when physicists write this, it's not strictly correct. But it's okay at the level of algebra, the Lie algebra, not at the level of the Lie group. So this is a slight sort of perhaps amusing remark. All the papers that you see when Weinberg talks about SU2 cross U1, you have to ask him whether it's the group he's talking about or the algebra he's talking about. Okay. So, okay, so this is just a quick few remarks to warm up. Now, I start with my book with a quote from D'Alembert. Could I erase this now?
Sure. I actually have a question.
Yes.
So in the sense of physicists, what is it exactly? Is it just multiplication of a matrix in SU2 times an element in U1?
Yeah, but it's not a direct product in the sense of mathematical definition.
You can multiply by something in U1 and you cannot get something with negative determinant.
Yeah, so for example, when you say SU2 cross U1, the element minus 1 belongs to both U1 and belong to SU2, so it's not a direct product. It's SU2 cross U1 slash Z2. You have to divide by some discrete group. Okay, so I wanted to start with this is how I start my book, D'Alembert, who died 6 years before the revolution. So algebra is generous. She often gives more than is asked of her. So when I saw this remark, I thought it's extremely French to say something like this. But when you study group theory, it really is striking that when you start with such simple definitions, you can get so much out of group theory. There's just so many beautiful theorems and so on and so forth. But when I read this remark, I was also quite puzzled why the French do not think that geometry is generous. And I guess geometry is not generous at all. And so I'm going to start talking about UN and SUN. And as I said, the key is that complex numbers comes in. So this requires contrast to SON. So for SON, the representations are given by tensors, which has many indices, let's say M indices, like this. And they all can be written upstairs but because of complex numbers, we need two kinds of indices. Upstairs and downstairs. So I'll now explain this because this, when I teach this course in the United States, students are often very confused why you need two kinds of indices. So let me emphasize that it is nothing profound at all. So in general relativity, as you know, in special relativity and general relativity, you also need two kinds of indices, the upper and lower, and but it's for a different reason. Here it's because we have complex numbers, and I will show very carefully how it comes about. So I'm going to follow a very lowbrow approach. This lowbrow approach is Feynman and also Landau and people like that. And Landau often refers to himself as a poor man, and it's the poor man's approach. Now, of course, you can be mathematically much more sophisticated and so on and so forth, and talk about contravariant indices and covariant indices. I won't do this here, but those of you who want to do that, you certainly can. And there's, of course, a deeper understanding in terms of vector space and dual space and so on and so forth. But I'm going to be very lowbrow, a la Feynman and Landau, and just write all the indices out, okay? So, in quantum mechanics and in quantum field theory, we talk about invariant objects. We want to construct invariants. And typically, you want this to be invariant. Objects like this, where psi could be a field or could be a... you want this to be invariant under some unitary transformation. And you want psi to transforms like psi prime is equal to u psi, where u is some unitary matrix. And you want psi star them to transforms like, just complex conjugate this equation, and u star psi star. Okay? So you can think of psi as a column vector and u as a matrix. And you want this thing to be invariant. You want it to be unchanged, not to change. Okay? So this you can write as psi. If you think of psi as the column vector, okay, as I said there, then this is psi star transpose. Or you can write this as psi transpose psi star. Okay. But psi transpose psi star, by definition, is psi dagger psi. So this is the inner product that you want to be invariant, and that's a basic postulate, of one of the basic postulates of quantum mechanics. So psi dagger psi U1 goes into psi prime dagger, psi prime is equal to psi dagger U psi, right? And by associativity, this is psi dagger U psi. And so we see that this is invariant if U is a unitary matrix. If U is unitary. So that's how we are motivated to study UN. But imagine that you were in the 19th century before quantum mechanics. Physicists would have no reason to study UN at all, just like the finance people have no reason to study UN. Okay? So we want this thing to be invariant. Okay, so what is this business of two kinds of indices? It's just a very clever notation, in my opinion. So this is the lowbrow approach. A very clever notation.
Anthony,
Yes.
Sorry, it's not a question as much as a request. Actually, there is, those of us in the back can only see the first half of the poem. So would you mind pushing it up as you write the first half?
Oh, okay. Thank you. Yeah. Is there a room with a better blackboard arrangement and so on?
yes.
So the students in the back would see better.
Oui, mais j'ai réagi.
Okay. So the very clever notation, and I insist I want to not talk about fancy mathematics such as dual vector space and contravariant and covariant. I want to avoid all such words like covariant, contravariant, and so on. But I just want to insist that it's a very clever notation. The clever notation is the following, and I actually don't know who invented this. That psi I complex conjugate we'll write as psi with a lower index, psi lower I. Okay? So this notation is very nice because if you do that, you see that this quantity, which is invariant, then become sum over I, psi I, psi I. The star is gone. So if you like, the notation is that instead of writing star all the time, you have upper and lower indices. And then you can write this as just psi I, and omitting the summation symbol. So this is one of Einstein's greatest contributions, right? People, physicists regard this as one of Einstein's greatest contributions. Sorry? Sorry? Einstein. Yeah. Well, it's at least attributed to Einstein. Well, I don't know. But in physics, it's called the Einstein's convention. So it's Einstein's repeated index convention. So Einstein realized that since all the indices would match in the sum, you can omit the summation symbol, and any index that's repeated would be summed over. Okay. So the rule is you always sum upper indices with lower indices. So this is exactly the same as in general relativity, and it's a really great rule because this, you find yourself, you catch yourself from making mistakes if you're summing upper indices with upper indices and lower indices with lower indices. Okay. So now, if we do this, we see that psi I goes into psi prime I is then uij psi j. And we want to sum over j. So now in this convention, the second index, which is the column index on u, goes downstairs. Now you see in a second why this notation is very nice, because the lower index would go into psi prime I, okay? But you see that this can now be written as psi j u dagger j I. And I, again, for some of you, you've seen this many times and so on and so forth, but for the beginners, people who've never seen this before, I ask you as an exercise to check this. So now you see the convention is such that all the indices match very nicely. Psi I psi prime goes into psi j u dagger j I u I k psi k, and you see that this becomes delta jk, the Kronecker delta, and so this becomes psi j, which is it goes into itself. So now here one could make a remark about the importance of convention. As you know, in physics, somehow convention makes a huge difference. And Einstein is a classic example. If you look at his early papers, he uses terrible, really terrible conventions. Because I also wrote a book about Einstein gravity. And so I looked up some of his original papers. So all of this repeated summation convention did not appear in Einstein's early papers, only much later. And in fact, it's incredible. Even in his early papers, he did not even use indices. There's no, you would think he introduced time and space as four-dimensional index, the way we now write x mu. But instead, it's he uses he writes out all the coordinates t, x, y, and z, and then the other observer on the train or whatever in special relativity, nowadays in all the textbook we use t prime, x prime, y prime, z prime or something. And Einstein also apparently never heard of the prime notation. So the time for the other observer, time is something like eta, and space is something like psi, kappa, c or something. He uses Greek letters. And if you read his paper, first of all, E equal to mc squared was not in the original paper. It was in a paper he wrote 6 months later. And then you never find the equation E equal to mc squared, because energy is not E, and the speed of light is something like u, energy is k, and so on and so forth. So Einstein only later realized the importance of convention. Now, convention is very important, as you probably know. Dirac, for example, as far as I know, he has only said, I wish something, only once, which is when he saw the van der Waals notation for the Lorentz group. And he said, I wish I had invented this notation, something like that. And so the van der Waals notation is now used by particle physicists in many contexts. Okay, so I'll continue. So can people see? Then there's a problem for people in the back if I push this up. So I'm going to go very quickly. I assume you know what tensor representation is. So now the representation of SUN could now be written in terms of tensors. So with, in general, m indices and m upper indices and n lower indices. And this is explained on page 233 in detail, so I won't explain it here. Okay. So for example, phi ijk, a tensor with two upper indices and one lower index, we go into phi prime ijk, and the indices transform independently, il, uj, m, phi, lm, and u dagger, and k, like that. So notice that the upper indices transform with u, and the lower index transform with u dagger. Okay. So the first point is that we can contract indices, an upper with a lower. So again, an exercise for the students to verify that phi ij, j, if, for example, in the example of this tensor, instead of writing the most general thing, just use this example. If you set k equal to j and sum over j, as Einstein implied in his convention, then you see that this object, which by definition is kj phi ijk, this transforms just like phi I. So the two indices that are summed over disappear, so to speak. And in everyday language, you could say that they eat each other or something like this, or they formed in pairs and disappear. So this is like taking the trace of a matrix, but generalized to tensors, in which you take two indices, set them equal, and sum. So this also implies that if you want to get irreducible representations of un, you have to subtract out the trace, subtract out the different traces. Okay. So because they transform by themselves. So the second remark is that the symmetry patterns among indices are preserved by transformation. By transformation. And what I mean by this, for example, in this example, is that if this tensor is symmetric under the interchange of I and j, then this tensor also would be. And the reason is, of course, the indices transform separately. And if it's antisymmetric in I and j, then this tensor will also be antisymmetric. In general, there would be some very complicated, you could have complicated symmetry patterns among the indices and will be preserved. So when you work out the irreducible representations, you can symmetrize and anti-symmetrize and so on. Again, the details are discussed on page 234. Okay, so I think you suggested that for the students, if they don't have the book, if they don't have my book, they could maybe Xerox some pages. And it's okay with me, but it's not okay with the publisher, but the publisher's not here. So my publisher is Princeton University Press, but my editor lives in Oxford, so she doesn't know.
Maybe I should not record what is there.
Oh, okay. So obviously I cannot explain this in detail, but only refer you to the appropriate pages. So the other thing is that in UN we can move the indices up and down by using two invariant symbols. And I call them symbols and not tensors. Some books say tensor, which I think is a very confusing use of word. It's really a symbol, namely the Levi-Civita symbol. epsilon I1, I2, IN, and there are two of them, one with upper indices and one with lower indices. Okay. I hope I pronounced it correctly. Levi Civita? Yes? Civita, okay. So you should put it in the emphasis on the first. Civita, okay. Levi Civita. So let me remind you, for the 3-index Levi Civita symbol is epsilon ijk, is totally anti-symmetric. It's defined that by saying that if you anytime you interchange a pair of indices, you get a minus sign, and epsilon 1, 2, 3 is equal to +1. So totally anti-symmetric. Epsilon ijk, for example, is equal to minus epsilon jik, and every time you interchange a pair of symbols. So this, I remember I was an undergraduate at Princeton, and I learned this at my second year, the first week of my second year. And I was quite amazed that such a symbol exists in physics and so on and so forth. So do you know the history? Did he introduce this? Why no mathematician before that used this symbol? Okay, so I hope I'm not going too slowly or too fast. As I said, I really don't know what the correct pace is at this, because this is a 5-week course and I want to get to Katang and Dinkin, so this is just going over some basic stuff very fast. Okay. Oh, I'm sorry, I forgot for the people in the back, I forgot to raise this. Okay.
You first.
Oh, first, I see.
Yeah.
Yes.
The notation of Einstein, was it for restraint relativity or for general relativity?
I think it's for both. At least that's how we use it. Now, I don't know the detailed history when it was really used, and when whether it was really Einstein or was just attributed to Einstein, that I don't know. Okay. Yes?
You said it moving the indices up and down. You say it's related to the epsilon?
Yes. You use the epsilon symbol to move indices up and down. So, for example, if I have phi ijk and I multiply by epsilon kln, then this is a tensor that is phi ijln. That's the definition of this tensor. And you see that it transforms like a tensor with 4 upper indices. The lower index has been moved upstairs. If this is U3, in the U3 example.
But in the case of the first psi, when we define the psi with the phi below,
Yes?
what should we do? We had the psi with the upper I,
Yeah.
and then we define the psi with the lower I.
Yeah. So, for example, if you are in, it depends on the group you're in. If you're in U7, for example, in SU7, then the epsilon symbol has IJKLMNO, right? It has 7 indices. Then, if you multiply psi I by the epsilon symbol, then it becomes psi JKLMNO. It becomes a tensor with 6 indices. Okay, so it depends on the group you're in, and this is important. So as you can see, if this n is even, it has some special properties because then it has even number of indices, and you can So, for example, for SU6, psi ijk, if you have some indices with 3 indices, and your ijk, lmn, this is like a tensor with 3 upper indices. So in fact, this is duality. This is a very basic form of duality. And it's very, again, something that seems very trivial, but actually very profound. So the example that we know is the duality between electricity and magnetism, between electric field and magnetic field. And why? So this not only works for SUN, for the SU group, but also for the SO groups, the epsilon symbol. There's only one epsilon symbol in the SO group. The difference is SUN groups have 2 epsilon symbols, and for the SO groups, the orthogonal groups, there's only 1. Okay, so the really sort of rather profound statement is that we also live in an even dimensional space-time. So SO4. So we live in SO31. The Lorentz group is SO31 for space-time, but by analytic continuation, it's SO4. So for SO4, it says that tensor with 2 indices is anti-symmetric tensor with 2 indices is isomorphic. It's dual to a tensor with also 2 indices. So this is the electric field and the magnetic field. Anti-symmetric tensor, in fact, is F mu nu. Okay, so in string theory, the same kind of thing happens. Okay, other questions? Yeah.
What is the difference between the 2 epsilon?
Oh, so numerically they're the same. They're symbols, so they're just they're either 0 or 1. They're not tensors. So, but the transformation property using our convention, one of them is associated with the lower index, and the other is associated with the upper index. Okay, and you must use the correct one. Yes.
Any particular reason why you need a completely anti-symmetric tensor to actually occur to indices?
Yes, yes, because so I'm going very, very fast here. So I some of these things that takes a few pages in my book I mention in 1 sentence. So the reason is because the determinant involves epsilon symbol. So it's when you transform the tensors, the fact that the determinant is equal to 1 has to come in. Okay, so that's why when we have SUN, the S means determinant equal to 1. Okay, that's a good question, which I that's actually a very good question. You have to sit down and work it out. My explanation is very sketchy. Other questions? Yeah.
Could you please tell why you do not move indices by delta chronicle?
Sorry?
Why you do not move indices by delta symbol?
Oh, the delta symbol. Oh, that does not move indices. That contracts 2 indices. Okay, when you multiply by the chronicle delta, you set two indices equal and sum over them. Okay, other questions? So so let me continue for how much time has passed? Oh, okay, so almost an hour. Yeah, so we'll take a break shortly. Okay, I'll go for 2 more pages, and then we'll take a break. How's that? Okay, so again, this is very, very, very sketchy, which is group to algebra. So from a Lie group to a Lie algebra. So this is explained on page 235. So we have to solve, for UN, we have to solve these 2 equations, if you like. Equation 1 and determine U equal to 1. Okay, that's the definition of SUN. So Mr. Lie had a great idea. So this is Lee's idea with a bow to Newton and Leibniz. So he said that these two equations are too difficult to solve, so we go to infinitesimal variations. And this is, of course, the great idea of Newton in inventing calculus. So Lee's idea is similar. He says instead of trying to solve it for the general U, we just let a U be, consider a U that's very close to the identity. So consider this matrix I plus IH, and put an I here for convenience, as you will see later. And then he said to solve this equation, you just plug that in, and U dagger, where this becomes minus IH dagger, right? If I Hermitian conjugate this, the I changes into a minus sign, and then times U, I plus IH, go to I. And since H is considered small, so then we ignore the quadratic term in H. So we just have the linear term plus order H squared. So this condition becomes H dagger equal to H. Okay. So so this is Lee's great idea. So one of the greatest ideas in mathematics ever. And then he said once he knows the solution for infinitesimal U, he knows how to build up, because of the group multiplication, you can always take this limit n goes to infinity. So if you know U as for infinitesimal transformation near the identity, you can perform the transformation a zillion times. So the way I like to put it about Lee's great idea is that if you have to do something, if you have to rotate, for example, if you perform a rotation through 19 degrees, so Lee says you don't have to rotate through 19 degrees, you rotate through 19 zillions of a degree, very, very small angle, and you do it a zillion times. Okay? So many of the greatest ideas in mathematics and physics are very, very simple. So this implies that if you multiply this thing n times, this implies U equal to IH. Now then the determinant, this equation, could be solved by taking the determinant of, evaluating determinant of U, if U has this form. So the determinant of U is e to the I trace H. Now there's a famous identity, which is the determinant of U, that if you have a matrix which can be written as the exponential of a matrix, the determinant of an exponential, okay, is the exponential of the trace, which I'm using here. I'm using this theorem. This theorem is, by the way, extremely useful. It's used in quantum field theory, statistical mechanics, Einstein gravity, and so on and so forth, Riemannian geometry. Determinant of U is equal to e to the I trace H. Okay, so I'm using exactly this here. And the quick way of proving this is that, again, if your students are seeing this for the first time, it's just you just diagonalize. You know that if H is a Hermitian matrix, it can be diagonalized. So if we diagonalize the matrix H, this U becomes diagonalized. The determinant is just the product of the diagonal elements, and trace of this is just the sum of the diagonal elements, so you can see that it just it works. Okay, so this implies that trace H is equal to 0. Okay? And this is all discussed in detail, page 236 of my book. So therefore, we learn Lie has solved the problem that the Lie algebra, which is what H, can be written as linear combination of traceless Hermitian n by n matrices. Okay, so Lie has told us that the group UN could be studied by looking at the algebra, which consists of these matrices. So immediately we give some example, and these are all famous in physics, very important in physics. For SU2, this traceless Hermitian matrices, a 2 by 2 Hermitian, 2 by 2 traceless Hermitian. And you can see that there are only, there's 3 of them, sigma 1 equal to 0, 1, 1, 0. So these are very important matrices in physics, which if you've taken a course on quantum mechanics, of course you know them. And they're called Pauli matrices. So I also assume that you know the properties of Pauli matrices, properties of these Pauli matrices. And this is on page 246. And so, for example, one of the things I expect you to know is that they anti-commute. That sigma 1, sigma 2 is minus sigma 2, sigma 1, for example. So for the students who don't know this, you should just read this page and learn about them, okay? So there's 3 of them. For SU3, there are 8 of these matrices, 8 3 by 3 traceless Hermitian matrices. And in particle physics, they're called Gell-Mann matrices. So I always tell the students that they could write down them the matrices for SU4, which would be the 4 by 4 traceless Hermitian matrices. But unfortunately, you're born too late to be named after you. I think it's very unlikely that physicists no longer name traceless Hermitian matrices after people. So now, when I was writing this book, my group theory book, I thought this Pauli matrices, it would be extremely surprising if the mathematicians did not know about Pauli matrices. And these days with Google, it's amazingly, in the old days I would have to go into some dusty library, for example, Princeton, which is full of bats and things like this at night, and all the journals would be covered, and there's no hope of finding it but with Google, it's amazing. So I found them in a paper, these matrices, I found them in a paper by Sylvester in a journal in 1882. So, of course, he was not concerned with quantum mechanics. He was not concerned with spin. He was trying to solve some matrix equations. So, but I'd like to tell a story about Sylvester, because then Sylvester, he was invited to lecture in the United States because the Americans have heard of these new things called matrices, which is supposed to be absolutely fantastic. And they don't know what a matrix was. So they invited Sylvester to come and lecture for a year. Sylvester was willing to come, but he did not trust the American dollar. So he demanded to be paid in gold. So that was the condition. So after 1 year, he after teaching the Americans what matrices were, he went back to England with a bag of gold. So I tell the story just to show that the mathematicians can be quite practical. Okay. Now, the second story is about about Gell-Mann. Now, Gell-Mann told this story. I actually heard Gell-Mann himself tell the story, and it has to do with French, so that's why I tell the story again. And I find it extremely hard to believe that because Gell-Mann is unbelievably, I mean, this is one of the smartest guys, one of the most intelligent guys in theoretical physics in our time, right? So he said he discovered SU3, trying to generalize the Pauli matrices. So the Gell-Mann 3x3 matrices, for example, you can see what the students, so as an exercise, you should write down the Gell-Mann matrices. But you can already see what some of them are. We can already write down 3 of them. 3 of them would be just the Pauli matrices and the 3 Pauli matrices with I equal to 1, 2, 3. So we already 3 of them. So you have to write down 5 others. Okay? So if you have 3x3 matrices, you just put the 2x2 here and put zeros there. You already have 3. Then you have to find the other 5. So he said that he took a sabbatical year in Paris in order to find the other 5. So he said every morning he would try to write down a few other 3x3 matrices, and he started to commute them and to find the other ones. Then the French guys would come and ask him to go to a long lunch with good wine and so on and so forth. And so he said that every afternoon comes back from lunch, and he tries to commute 3x3 matrices, and then he would fall asleep from all the wine. So every day he has to repeat this process. And it took him a whole year to find the other 5 matrices, which I find extremely difficult to believe given Gell-Mann's intelligence. Even allowing for the fact that everything in physics sounds simple in hindsight, 40 years later it sounds trivial to write down 3x3 traceless Hermitian matrices. But the punchline, when Gell-Mann tells the story, and Gell-Mann tells the story very well, I cannot possibly match the way he told the story, is that he said the French guy who asked him to go to lunch was the world's greatest authority on Lie algebras. And if only the French guy knew he was commuting 3x3 matrices, the French guy would have told him what those matrices were. But he never asked the French guy. The French guy never asked him what he was doing. So he claims he spent a whole year to discover SU3, which I find extremely. But I just want to tell the students, because these days mathematics has become so advanced, people doing string theory use all kinds of really fancy mathematics, that it's amazing the level of mathematics in physics has gone up. So when I was a postdoc in Princeton at the Institute for Advanced Study. And the year I was a postdoc, I wrote a paper with 2 other young physicists, Karlitz and Michael Green. Michael Green is the Green of doing string theory later. He's the author of the textbook on string theory with Witten and Schwartz. And we wrote a paper using Gell-Mann's SU3. So with 3x3 matrices. And that particular year, Jeff Chu was spending a sabbatical year in Princeton. He was visiting from Berkeley in the physics department. So one day we got a phone call from Jeff Chu, and Chu is the contemporary of Feynman, Gell-Mann, and all these people. So Jeff Chu is one of the most famous people at that time. So the 3 of us went to, he asked the 3 of us to go to his office to explain our paper to him. And he was quite angry. He said, 2x2 matrices, Pauli matrices, they're good enough for Pauli and Heisenberg, and that's what I've been doing all my life. Why do you young people have to write down 3x3 matrices? So you see the level of mathematics, how it has gone up. So anyway, this is a good time to take a short break. 10 minutes? 10 minutes?